So in these slides we want to see what happens if both things happen at the same time, that the magnetic field changes with time and also that the wires are moving. So let's start again with the general expression for the force on a charge. The force on a charge is QE, the electric force, plus QV cross B, the magnetic force. And if you divide then F, force per unit charge, it's E plus V cross B. So the EMF, the definition of the EMF, it's the integration of the force per unit charge dotted into the element of length on a closed contour that the wire exists on. And we said before that it can be shown that this is equal to the work per unit charge over a complete path that the charge moves on. Now, if you put F over Q to be E plus V cross B, remember there are two kinds of electric field. There's the static electric field due to static charges, and which is the conservative electric field, and there's the non-conservative electric field that happens because of changing magnetic fields. So if we shoot that into there, we get these three expressions. Integration of the electric field due to static charges, the conservative electric field, over any closed loop is 0. Go back to the previous videos to see where this comes from. So we can put it to 0. Now, integration of E non-conservative dot ds around the closed loop, we showed before, this is the Faraday-Maxwell equation. It's minus integration of partial B by partial T dot dA. So we can replace this by that. We can replace integration of V cross B dot ds, where V is the velocity of the charge, the total velocity of the charge, by integration of the V of the wire cross B dot ds. So we know this expression also from before. So we can then say that the EMF, in the case where you have a change in magnetic field with time and you have wires moving, you have to add these two parts together. Now, it can be proven mathematically that when you add these two things, it's the same thing as taking the negative of the derivative with respect to time of the magnetic flux. So it's a very strange thing that the EMF is always equal to minus d phi by dt, no matter what the cause is. Whether the magnetic field is changing only and the wires are fixed, or if the wires are moving and the magnetic field is constant in time, or if both things are happening at the same time, the magnetic field is changing with time and the wires are moving. It doesn't matter what the reason is, but always the EMF is minus d phi by dt. Now this proof, we're not going to do it in this course, but in a more advanced course you can do this kind of proof. But at least you know now where things come from. Remember again why the magnetic flux, when you take its derivative with respect to time, you get these two terms. Remember from this simple example where you have a rod moving on two conducting rails with a certain velocity. If you take the rate of change of magnetic flux, in this simple case, it's the rate of change of B times A. And that means you get two terms. One term has A dB by dt, another one is B dA by dt. So this term is the one that happens because of the magnetic field changing with time, and this one happens because the area is changing with time. So the magnetic flux can change due to two reasons. One, if the magnetic field is changing with time, and one, if the area is changing with time or the wires are moving. So to summarize, the EMF, the basic definition, and you can prove that the EMF is always equal to minus d phi by dt. So this is called the EMF flux rule. And this applies no matter what the reason is, whether the changing magnetic field only or the wires are moving or both.